Hey everyone, I'm Won Lee. Today, the topic is test hypothesis for the difference of paired data. Previous lecture topic, test hypothesis for the difference between two independent populations. So, can you catch the difference? We have studied this kind of things in chapter 4, estimation. So, same thing, what happened in test hypothesis? It is not much different, actually. Let's see. Test the hypothesis for the difference of paired data. It is like a one population problem. As mentioned earlier in chapter 4 on estimation, paired data refers to the scenario where there are two sets of data for a single entity. For one person, for one objective, we have two set of data, such as weight, before and after diet, before diet, after diet weight for one person, height of fathers and sons in one family, father height and grown up son's height in one family, and the debt ratios of companies from last year and this year. So for one company, last year's debt ratio and this year's debt ratio. Okay, let's. Is there any difference? We want to know like that kind of thing. The distribution of such data involves joint probability distributions, which represent a completely different problem compared to the case of two independent groups discussed in section 5.9. Okay, so you have to know what is your problem, what do you want. So the what method of sampling method may be different. Okay, from two different population we get samples, or for one population they are two set of data. Okay, for one entity, one person, or one objective. Paired data consists of two datasets x, y, but when transformed into differences d equal to x minus y, then this is a difference random variable. It becomes a problem of determining whether the mean of difference d is 0 or not. There is no difference or difference. In other words, h0 mu sub d. Okay, now the random variable is d. So mu sub d equal to 0 versus h1, mu sub d is not equal to 0. There is a difference. Thus, the paired data problem becomes a hypothesis testing problem for a mean of a single population d. Understand that? Now, the tested statistic and each distribution, tested statistic is what? Sample D1, D2, Dn, its mean, D bar, tested statistic. And it follows normal distribution with the mean mu d and variance sigma d square over n. Okay? So one population problem. So rejection region for H0 it will be this one, and equivalently we can see this kind of a thing as in one population test hypothesis problem. It is simple, okay? Okay, let's see, example. There is one population problem, but in using computer, you treat one population problem as paired data problem. Let's see. Tenure days of new employees at a financial company are said to follow normal distribution. Okay, this assumption, this assumption from due to the small sample, 9 sample. So I need this normal distribution assumption. The tenure days for 9 new employees who left the company were as follows: 2000, 1975, 9 datas. can it be said the tenure days for new employees at this financial company exceeds 1950 days? Okay, so H1 is mu greater than 1950. The null hypothesis H0 and H1 is like that. And you may say this one, H0, 1950, without the inequality, less than inequality. Okay, that is okay. But in theory, the parameters cover all real value range 1950, then greater than, the other one is less than equal to 1950, cover all real numbers. That's why this one is for theory, for formal, but many persons just say 1950, just equal to 1950. This problem is fundamentally a hypothesis testing issue concerning the mean of population, right? One population problem. When using software, computer, the computer treats it as paired data to solve the problem. In other words, values obtained from the sample are treated as pairs. 2000, 2000, paired data, 1950, 1975, 1975, and 1950, paired data. Okay? So there exists, when using computer, t-test is very useful, famous test statistic, and you get p-value from t-value. Observed t-value, you will get p-value, significance probability, and it depends upon the magnitude of p-value, you make decision. You reject H0 or H1. Okay, so from this one, this is a result of from computer output. T value will be 0.7184, small t value. What is the degrees of freedom? Degrees of freedom here is what? What? 8, right? 9 samples. Sample size 9. So n minus 1, 8. P value is 0.2465, 24%. Since then, H0 cannot be rejected. We do not say H0 is accepted. Okay? H0 say cannot, is not, is not rejected. So the hypothesis, your hypothesis is what? Your claim, the company's claim. Companies has this kind of a claim. Financial, that company exceeds the tenure days for newcomers exceeds 1950. If your hypothesis is that, then your hypothesis is rejected. Same thing. Okay. However, if a report states hypothesis as the tenure days of new employees at this company exceeds 1950 days, that is your hypothesis, then this is actually referring to the contents of alternative hypothesis as the hypothesis. So your hypothesis is rejected. Not confusing? Okay, another example. To determine whether there is a difference in durability between running shoes A and B, 10 individuals were selected and asked to use shoes A and B for 2 months each. Okay? Afterward, the remaining lifespan of jogging shoes A and B were measured. We okay? We aim to perform a hypothesis test to see if the durability of shoes A is superior. Okay, let's see. H1 is mu A is greater than mu B. We aim to perform the hypothesis test to see if the durability of shoes A is superior. So the remaining lifespan is greater than uh, B. H0 will be mu A equal to mu B. Okay? So one-tailed test. Then we get real sample values for person 1, 27, 23, 35, 28, up to 17, 16. So it is paired data problem. So we need 1, 2, up to 10 persons, okay? And let them use the shoes A and B. All right. So result from computer t-test output, test statistics 7184, p-value 0.493, something like that. So real p-value for your test hypothesis should be what? 0.493 divided by 2, because this is one-tail test problem. Your problem is one-tail test problem. But usually, computer program calculated two-tailed test p-value, because some software program may command this kind of a hypothesis, but usually computer program provides you two-way p-value. This is two-tailed p-value. So we have to divide by 2 this result for one-tailed test. This problem should be viewed not as a test of differences between two independent groups, right? But rather as paired data where each person uses both A and B. It would not be advisable to consider this as a problem of testing differences between two independent groups by selecting what? 20 different individuals. We need 20 persons. 10 here, 10, oh, sample size 10 from A, sample size 10 from B. But testing 10, A and 10 with A and 10 with B. Okay, this is because the conditions such as individuals' behavior habits in using shoes differ and are difficult to control consistently. We cannot control the individual's lifetime or habit, that kind of thing. So this is typical paired data problem. So if you know what you want, what is your aim, goal, then you have to select uh, depending on your goal, aim. Okay? Okay, that's it today. Thank you. Bye.